Taylor is playing a computer game in which they shoot at spaceships and battleships. The mean number of spaceships they hit per minute can be modeled by a Poisson distribution with mean 4.2. The number of battleships they hit per minute can be modeled by a Poisson distribution with a mean of 2.3. Any single hit occurs independently of all others. Letter A, find the probability Taylor hits at most 10 spaceships in 2 minutes. Looking at spaceships, let's represent spaceships by the letter S, follows a Poisson distribution with mean 4.2. So they hit 4.2 spaceships per minute. But in this case, it's 2 minutes. So if it's 2 minutes, then we multiply 4.2 by 2 to get 8.4. So our variable S follows a Poisson with mean 8.4, not 4.2, 8.4. And then we want to know the probability that Taylor hits at most 10 spaceships. At most 10 spaceships means that he can hit a maximum of 10 spaceships. So we want this to be the variable S to have a value which is less than or equal to 10. And then we are going to use the calculators to find this probability. In Texas, we go to distribution by pressing seconds and the key vars. Then we look for Poisson cumulative, Poisson CDF. Then we select Poisson CDF. We insert the mean 8.4 and then the value 10. The calculator will sum all the probabilities from 0 up to 10 and give this result. 0.774 to 3 significant figures. So we write this down, 0.774. In TI-Nspire, we go to menu, and we select probability, distributions, and then we look for Poisson cumulative, Poisson CDF. The mean, 8.4, and the bounds starting at 0, going up to 10. That's the value using Nspire, the same value we found using TI-84. Here we go to menu distribution, and then we select Poisson. Tail is the first tail because we want to be less than or equal to 10. The X value is 10. The mean is 8.4. The same value. We have done part A1, now going to part A2. In part A2, we have to find the probability that Taylor hits a total of more than 10 spaceships in 1 minute. So we have now 2 variables, and then we want to add them. Let's say the variable S now follows a Poisson distribution with 4.2, and the variable B follows Poisson distribution with mean 2.3. When we are adding the variables, the variable S plus B follows a Poisson distribution with mean 4.2 plus 2.3, which is equal to 6.5. So we want to know the probability that this variable S plus B, the probability that S plus B is greater than 10, knowing that the mean is 6.5. Going to the calculators, we're going to need to find probability of S plus B is greater than or equal to 11. So now let's see how to find this in the 3 calculators. This time we go to distribution, Poisson cumulative, we put the mean 6.5 with a value of 10 because we want to be greater than or equal to 10. When we do this, we find the probability of being less than or equal to 10. So we have to do 1 minus this probability, which is 0.0668 to 3 significant figures. So here in Texas, whenever we want to find the probability of being greater than a number, greater than or equal to a number, we have to do 1 minus the probability of being less. Here in Casio, we go to Poisson, and this time we select the other tail by pressing F3. We want this to be greater than or equal to 11 when the mean is 6.5. We get the same answer. We go to Menu, Probability, Distributions, and then we look for Poisson Cumulative. The mean is 6.5, and then lower bound, I'm gonna put 11. And for the upper bound, a large number, let's say 200, a number that is far away from 11. So when we calculate this, we get the answer. Every spaceship that is hit earns Taylor 3 points, and every battleship 5 points. Let C be the total points earned in 1 minute. Find the expected value of T and the variance of T. Remember that the variable S represents the number of spaceships per minute with a mean of 4.2, and the number of battleships, Poisson distribution, mean 2.3. Here, the variable T is 3 times S plus 5 times B, because for every spaceship hit, Taylor gets 3 points and 5 points for every battleship that is hit. So the definition of the variable T is here. So we need to find the expected value of T and the variance of T. To find the expected value of T, we need to look at the formula booklet to this formula, linear combinations of any independent random variables. The formula of the expected value is here, and also for the variance. For the expected value, it's a linear combination. Whenever we have expected value of A1, X1, A2, X2, it's A1 expected value of X1 plus A2 expected value of X2, and so on. Applying this to the variable T, this is the same as 3 times the expected value of S plus 5 times the expected value of B. The expected value is the mean. So the mean of S is 4.2. The expected value of S is 4.2. And also, the expected value of B is 2.3. So we place these values here. So do 3 times 4.2 plus 5 times 2.3. Then we do this calculation. The result is 24.1. This was part B1. To do part B2, we want to find var of T, which is, according to this formula, A squared variance of X1, A2 squared variance of X2. So applying this to our variable T, this is going to be 3 squared var S plus 5 squared var B, which is 9 times the variance of S is the same as the expected value. Remember that in a Poisson distribution, the mean is equal to the variance. So the variance is 4.2 plus 25 times the variance of B, which is 2.3. Using a calculator to find this value, this gives 95.3. And then the letter C, state one reason why the distribution of T cannot be Poisson. And then the reason is because exactly the mean is not equal to the variance. Because if it were the same, then it would be a Poisson distribution. So since the expected value of T is different from the variance of T, then as a conclusion, T does not have a Poisson distribution. And that's the reason that we should write to justify that it's not. If it were the same, if the expected value and the variance were the same, then T would follow a Poisson distribution. Taylor intends to play the game for 1 hour. Letter D, use the central limit theorem to find the probability that Taylor's mean score per minute is greater than 25. He's going to play for 1 hour. 1 hour is 60 minutes. So now we have the variable T with expected value 24.1 and variance 95.3. This for every minute we have this mean for the variable T and the variance 95.3 for the variable T. The central limit theorem states that if we do this many times, like 60 times, using the central limit theorem, we can say that the mean of T bar, will follow a normal distribution with mean 24.1. This is the mean, the expected value is the mean. Then the variance of the mean of T, according to the central limit theorem, has variance 95.3 divided by 60, because we're going to have the variable T 60 times, a sample of size 60 of the variable T. Then with these values, we can now find the probability that T bar is greater than 25. And then I'm going to show how to do this using our calculators. Here in Texas, TI-84, we need to go to distribution and then normal cumulative. Our lower value is going to be 25. Upper, we can choose any value large enough, 10 to the 99, for example. The mean is 24.1. And the standard deviation is the square root of 95.3 divided by 60, because 95.3 divided by 60 was the variance. Here in the calculator, we need to insert the standard deviation. So that's the probability, 0.238 to 3 significant figures. 0.238. Go to menu, probability, then distributions, and then normal cumulative. The lower bound is 25. Upper bound can be any large number. The mean, 24.1. And the standard deviation, we're going to put square root of 95.3 divided by 60. And then that's our result, 0.238. We go to normal, select this tail greater than or equal to a number, x value 25. Standard deviation is square root of 95.3. Let's put this in brackets, 95.3 divided by 60, with a mean of 24.1. Execute 0.238.